Sarah, who's a assistant professor of analytics and operations management at Bucknell University. He got his PhD from CMU. We also got the Gerald L. Thomas Doctoral Dissertation Awards in Management Science. He worked on a variety of applications and theory of optimization, but today he's going to talk about an NSF project that he's on, which is on compressing neural networks with discrete optimization. Very excited to have you here. Please go ahead.
Well, thank you very much for the introduction. Well, it's great to be here, great honor. And today I'm going to talk with you about this work where for the first time, we were able to put together two things that are very dear to my heart as someone who likes discrete optimization. And I guess this audience, I would have some more people that are like that. One of them is the problem of making neural networks smaller, either compressing them or just removing their parameters. It's a problem that perhaps we understand what the decision variables are, but I am not that sure about the objective function. So every paper that we work on that, we're trying to optimize for something slightly different just to see where we get with that. And then there's a second stream of work that really interested me coming from discrete optimization, which is the theory of linear regions, which is just one way by which we can try to understand which architectures for neural networks are capable of expressing more complex relationships. And in this work, we're just basically going to see this both together. And just to make sure that we're on the same boat, and this is, I think I'm too far away. All right, we're good. So just to make sure that we're in the same boat, when I'm talking about a neural network here, I'm going to be thinking about, well, a stack of layers. Every one of these layers have neurons that are represented here by dots, that they behave basically like biological neurons in that they observe inputs. Sometimes they get activated by what they see, and they send a signal forward. And in this example here, we have a picture, and we want to tell whether there's a cat or a dog. So the neurons at the bottom of this neural network, they're seeing the picture. Some of them are getting excited, they're saying white, and they're sending something forward. In the second layer, those neurons are seeing what the first layer said, and they're transforming that further all the way to the point where we have supposedly a prediction. And the way that we're going to train a neural network for different tasks is that we adjust when these neurons get activated and what is the output that they produce for different samples so that we can have a good performance in whatever we want to do. Now, this is a very beautiful depiction. I'm not talented like that. So from now on, whenever we see a neural network, it's going to be a little more boring, a little more like a bunch of dots and arrows between them. And the way I like to think about neural networks is that they're mapping from an input space X all the way to an output space Y. And here we're going to think about neural networks using the ReLU activation, rectified linear unit, which is a very simple one, but also turned out to be a very effective form of activation using neurons. So for the past 15 years, this has been the most commonly used one. And in a ReLU, we have either 0 coming out, which is when we say that the neuron is inactive based on the inputs that the neuron is receiving from the previous layer, or the neuron is active and it's producing a positive value. And just to make sure that we're all in the same boat here, I just want to emphasize a little bit more what each neuron is going to do, because that also makes us understand the big picture a little better. So each neuron is going to basically do two things. One is calculating a linear function, basically like a linear regression. For each input that neuron receives, there is a coefficient. That's what we call the weights. And then we also have a scalar, which is the bias. So we're basically calculating the output of this linear or affine function, if you want to be more precise. And the second step is we take the maximum between that and 0. Now, if we have an input that produces a positive value, we send that value forward. If we have an input that produces a negative value for this affine function, we just send 0 forward. And I find it quite puzzling that sending nothing in that case, as opposed to sending whatever you calculated, can actually produce a very sophisticated model. And the way I like to think about this is that this is because silence speaks. Sometimes just not saying something means that you're saying a lot. And we're going to go back to that later when we talk about linear regions, at least my take on why that is so important. Now, for today's talk, we're going to cover three things. We're going to start by just giving you an idea of network pruning and optimization. So we're going to cover some basic definitions about what we do in network pruning. And I'm going to touch on some approaches we have tried in the past in case you're interested. And there will be references at the end about those. Then we're going to dive deeper into linear regions. And I'm going to get to a point where I'm going to say why I think that silence speaks so much and why that's so important. And finally, we're going to put these two things together and figure out a way to prune more neural networks without affecting accuracy as much. So we're going to start here thinking about how we can get rid of part of the neural network and still get away with that. So network pruning is this problem where we start with a fully connected or at least a dense neural network that we want to simplify. And there are two decisions we want to make. First, we want to decide that we want to remove some connections. For a neuron that would amount to setting some of the weights to 0, which means that some neuron from the previous layer doesn't influence a neuron from the next layer anymore. And the second decision that we want to make is how can we update the remaining weights so that the model is functioning very well? Because, I mean, if you're removing connections, that's altering the outputs, and you do want to do some fine adjustment. Typically, that is done by just doing a little bit more of training that we call fine-tuning, and we're not going to cover that so much. There are alternatives, but we're not going to discuss them in this talk. And there are some interesting facts about network pruning. The first one is that if you just do a moderate amount of pruning, and depending on the neural network, this can, and the data set, this can be 30%, 50%, or 75% of the weights, we actually get better accuracy. And so what we see here in this plot that's from like an important survey in this subject is, as you see this green line here, accuracy goes up as we prune more, and then suddenly drops if we just prune too much. And at the same time, when you look at the performance, just because we are zeroing out these parameters, it actually gets quicker to calculate. And the other thing that we have observed, and this was a paper we published last year at NeurIPS, is that the accuracy or like the performance of the neural network gets more evenly distributed when we do pruning. So in this case here, we were looking at a ResNet in CFAR10. And what you can see here with this intensification ratio alpha is we were calculating the balance between performance for each class, which is what we call recall, compared to the accuracy for across all the classes. And when the intensification is smaller than 1, in the way that we defined it, it means that we're actually distributing the performance across the class. So we get a more evenly distributed performance. And if we're moderately pruning, we gain accuracy and the performance is more uniform. So, which brings the issue of fairness to the front. Now, curiously, one of the most effective ways to do a quick pruning is just picking the weights with the smallest absolute value and getting rid of them. And this is what we call magnitude pruning. If we look at more sophisticated approaches that have been proposed in recent years, for example, lottery tickets were first validated using magnitude pruning as the basic step. There are, of course, some contenders that are a little more sophisticated. One of them is gradient pruning. So when we're training the neural network, we're optimizing for the loss function. We're trying to adjust so that we perform well on a labeled data set. And if we just take the gradient of the loss function and look for the parameters that have the least influence in the loss function, that's another way by which we could prune the neural network. That typically doesn't work as well as magnitude pruning, perhaps among other things because when we're training the neural network, we're hoping for the gradient to converge to 0. So another thing that we can try to do is look for second order expansion of the loss function, because we may assume that the first term is going to be approximately 0. If we're doing small perturbations, zeroing out small things, we can ignore the cubic term. And that brings to us a combinatorial problem. Because now when we're making decisions about about which weights to prune, which are the ones that we're going to set to 0, we're going to have elements in the objective function that are going to be account for weights that are pruned together. We explored this in a paper last year, and that led to a quadratic objective function and billions of binary decision variables. So it was not something we could solve with just MIP, but definitely if you look back in MIP in the 80s and all the heuristics and local search strategies, there are lots of good ideas there that helped us with this problem. And finally, there are also some opportunities for free lunch. For example, we may find some neurons that we can just remove from the neural network with little or no adjustment. For example, if we identify neurons that are stably inactive, meaning that no matter which input is sent through the neural network, they're never going to produce a positive value, we know we can just get rid of them because they just don't influence anything anymore. At the same time, we may have stably active neurons. If we have an entire layer that's stably active, we can just define the inputs to the next layer linearly And by that, we can directly wire the previous and the next layer and basically fold this layer of the neural network. Now, detecting stable neurons is something that we can do with mixed integer programming. So it's one way by just maximizing and minimizing outputs given the inputs that are valid for the neural network. But one thing that we observed with time was that if you're finding stable neurons, probably there's some problem with the architecture or with the loss function as it was defined, and we can actually prevent that from happening with a different type of regularization. So that concludes the first take at what I call network pruning. And we're going to look now at what I promise you should be the main thing, which is linear regions. So, and the idea here is that we just want to understand how a neural network can be so expressive and behave in different ways for different inputs. So if we think about the ReLU again, for each one of the neurons of the neural network, we're going to have two different phases. We're going to have a phase where if that first linear function calculated is negative, we're just going to output 0. If it's positive, we're going to output exactly what we got. So this is basically a piecewise linear function, one of the simplest possible piecewise linear functions, where you just have 0 or the identity when you cross the axis. And if you just compose a neural network with lots of ReLUs, you're basically composing a piecewise linear function with many more pieces. But the exact number of pieces is up to the debate depending on how you stack these neurons in different ways. And I find it very interesting because when we get to this point, we can think, okay, whenever I'm training a neural network that only have ReLUs, I can say that what I'm actually doing is a piecewise linear regression. And we don't know exactly how many pieces we have or how many we want. But one thing we might intuitively think is that the more pieces this function has, the better we can fit the data that we're observing. And there are two things that we don't know perfectly, but that we're working on. The first is, what piecewise linear functions can we get given different architectures? And the second one is whether we cannot find a simpler neural network that could do the same thing for us. And when I'm talking about these pieces, each piece of a piecewise linear function corresponds to part of the input space where the behavior of the function is linear, right? Each one of these lobes here. So in terms of the input, in neural networks, this is what we call a linear region. And one way that we can define these linear regions is by which neurons are active or inactive in the neural network. So for example, let's say we pass an input X through the neural network. That input X is going to activate some neurons in the first layer. And depending on the output of these neurons, we might have some neurons activating the second layer. Well, different X's may activate the same set in the first layer, but a different set in the second layer, and so on and so forth. So each input is going to basically give us like a footprint of which neurons get activated or not. And if you think in terms of a brain, whenever you do research and do MRI of brains, you might see different parts of the brain being more active if someone is listening to music, or someone is reading, or seeing a picture of a dog or a book or something like that. And now what we can say is that every linear region is going to correspond to a particular pattern of neurons being active or not. And with that in mind, we can say that well, in the best possible scenario, if you want to have lots of linear regions, you can have 2 elevated to the number of neurons, linear regions, because that would correspond to every neuron being on or off. But in practice, we don't get that much. And because there's some considerations about geometry that come to play. And I find that the most beautiful part about neural networks that I have learned so far. So, if we just can like restrict this maximum number of linear regions depending on the architecture, we might be able to compare different neural network architectures. For example, we can find limits to what functions can be approximated. We know that a neural network can be a universal function approximator, but of course that depends on having sufficient width or sufficient depth depending on the function. And also we can compare different configurations. So when we get to the end of this part, we're going to go back to this figure here. Here I have 2 configurations that I'm comparing. Both of them have 3 layers, and they're supposed to work on MNIST. In both of them, we have 22 neurons in the first 2 layers and 10 neurons for the output in the 3rd layer. And what is different about them is that in the first one, we have 18 neurons and then 4. The second one, we have 4 neurons and then 18. And it turns out that the average number of linear regions that you can get with the neural network on the left is orders of magnitude above the maximum that you could ever obtain with the configuration on the right, for reasons that we're going to discuss next. So when we talk about the geometry of the linear regions, the first thing you have to have in mind is what we call an activation hyperplane. So we have that linear function inside the neuron that's going to produce a positive, negative value, or maybe 0 if you're at the boundary. If we just equate that function to 0, we're going to define a hyperplane. And this hyperplane is defined on the inputs that are observed by a neuron. So in the space of the inputs that come to that neuron. And on one side of this hyperplane, we're going to be points that are activate the neuron. On the other side of this hyperplane, including the boundary, we're going to have the points that do not activate the neuron. So basically, for all the inputs that the neuron can observe, we're slashing into two half spaces, one where the neuron is active, another one where the neuron is not active. Then if we just think about an entire layer, it's a bunch of different neurons, each one defining a different hyperplane. All of those hyperplanes are in the same space, which is the inputs that they can receive from the previous layer or from the input of the neural network if it's the first layer. And the number of regions that we can define by that, the number of different of full dimensional regions that we can get out of that is going to depend on two factors mainly, which is the number of hyperplanes, which corresponds to the number of neurons, and the dimension of this space, which corresponds to how many inputs we're getting in this layer. And if we look at a shallow network, that's actually all that we need to understand the maximum capacity of this neural network. Let's say that we're thinking about a single layer, 4 neurons, and 2 inputs coming to this neural network. If we're thinking about the number of linear regions here, we're basically asking, okay, if I have a 2-dimensional space, how can I draw 4 lines and maximize the number of regions that I create? And the answer to that is that the maximum that we can do is 11. So, I mean, if you think about the bound that I mentioned before, if we're thinking about, we can have a region that's to the left or to the right of every line, that would be 2 elevated to 4, which is 16. But in a 2-dimensional space, there is no way we can draw 4 lines and get 16 regions. So the best that we're going to get is 11. And this is going to happen when these lines or hyperplanes in general are in what we call general position, meaning that you don't have any vertex being defined by more than the minimum number of hyperplanes meeting there. The converse of that, which would be lots of lines crossing at the same point, would be what we call degeneracy in linear programming. So with that out of the way, we know how to characterize this for shallow networks, and we know that there are ways to organize the neurons such that we can achieve this maximum number. When we talk about deep neural networks, things are a little more complex. And here we have another example with 2 inputs. Because we're all limited 3-dimensional human beings, we can only understand in a flat surface something 2 dimensions at best. So that's why we're going with that. But we can extrapolate based on what we observe here. So let's say we have these inputs x1 and x2. And then we have 3 layers. In the first layer, we have neurons A and B. If you see the leftmost chart, we are seeing the region where neuron A is active, which is towards the top, and the region where neuron B is active, which is also towards the top. And then we also have here the activations for C and D and E and F according to what they see. So the neurons in the second layer, C and D, they see A and B. They don't know x1 and x2. They only see things interactively. Same thing for the third layer. Now, what's interesting here is what happens when we think about the output being produced by each one of these linear regions, which are going to be further partitioned by the next layers. So when A and B are active, we have 2 positive values coming out. So the output is 2-dimensional. When only one of them is active, which is what happened in the gray areas over there, we have a 1-dimensional output because one of the values is just 0. And when none is active, basically all the inputs are mapping to 0, 0 in that layer, which means that from that point on, you cannot distinguish between points in this lower triangle here, because they basically are the same for the next layers of the neural network, which is perhaps a good reason why you may want to do some extra connections to regain that ability in more sophisticated architectures. But the most interesting thing is what happens when we try to think about these activation hyperplanes for C and D in the regional space x1 and x2. These activation hyperplanes are going to break each one of these linear regions in further pieces, but based on the outputs that they're seeing, not the input. And when they go from one of these linear regions to the other, they will start bending around. It's basically like light going through different media. You basically like have refraction there, like the angle is changing. And it's not a coincidence that when we look at the regions that were one-dimensional, that these lines are parallel to one another, because that space, you have less ability to separate, distinguish points in that space. And in the two-dimensional space, we can actually make a better distinction. And in terms of the dimension of the output, we're also losing a lot of dimensionality here. There are lots of places where we have 0 dimensions, many places where we have 1 dimensions, and only one region where we have full dimension, 2 dimensions coming out. And this will keep going on going forward. And this loss of dimensionality, it's something that we captured, like, it was basically my first work in neural networks. Realize, okay, if we're losing dimensions all over the place, these hyperplane arrangements in most of the linear regions are going to be much less expressive than anticipated. And that took us to this upper bound the number of linear regions, which, forget about it, it's just too much for a talk. What really matters is the consequences that we can get from these bounds, from these calculations. So, and one thing that we did was, what if we wanted to design a neural network with 60 neurons? And we chose 60 because 60 divides by 2, 3, 4, 5, and 6. It's convenient. Should we put all these neurons in one layer of 60 neurons? 2 layers of 30 neurons each, 3 layers of 20, and so on. Like, what would be the best thing according to this number of linear regions that you can define? And here we're comparing what we got on the left with the best possible, with the upper bounds that were known by the time. Both of them are the same for a shallow network, 16 neurons in one layer, basically because this is a tight bound. There's nothing to improve here. When we talk about 2 layers, 30 neurons each, and we keep moving on to 3 layers, 4 layers, 5, and 6, things are a little different now. So there are 2 things that are interesting here. First is that now we know that if the input dimension is very large, if you have more inputs than you have neurons, the best configuration, if you want to maximize this number of pieces in your function, is actually to have a shallow network. Because we know that the bound for that we can achieve that bound, the red line, and it goes above everything else. But the other thing that kept me thinking was, well, if we fix an input dimension, have a particular application in mind. Let's say my input is 15 or 12. Well, if you look at this upper bound, you see that, well, the shallow one or the deepest one is maybe not the best choice. Maybe, for example, 3 layers would be a slightly better choice. Now, this is all theoretical. At the time, and there are 2 things that we didn't know exactly. First, do these bounds connect very well with what happens in practice? And 2, do they provide meaningful information for us? So with regards to the first, we did compare these bounds with what the actual number of linear regions. And now, one thing that you may have seen, I mean, it's actually, there are many papers now working on this. You can formulate a trained neural network as part of a MIP formulation. And by doing that, if you just try to count the solutions on the binary variables of this formulation, you can count the number of linear regions of a neural network. And that takes forever. It's because in optimizations, in integer programming in general, we never care about finding all the solutions for a problem. We care about finding the best possible solution. So there is very little research on counting solutions in MIP formulations, understandably. Well, we did that. It took a very long time for a small network. But what was interesting, and this is where we go back to those configurations I mentioned before, is if we're talking about the configuration 4, 18, 10, that is the upper bound. If we talk about the configuration 18, 4, 10, this is what we observe in practice, way more linear regions. And the reason for that, as we have been walking through in these previous slides, is because of the geometry. If you start with a layer that has only 4 neurons, that means that the outputs are all constrained in 4 dimensions now. It's just harder to separate different points if you are limited to that space. You may have layers that are wider later, and it feels like you have a wider space, but all the inputs that are going to come through it are going to produce outputs in a very limited subspace. So it's not going to help us do a much better job. And we did back in that paper, we also did some preliminary work on what about the accuracy. So we looked at the training error and the test error and compared that with the number of linear regions. We did have to exclude pathological cases where one of the layers is just too narrow. Because let's say if you have 20 neurons in one layer, 1 in the next, the number of linear regions is high because you're just defining lots of linear regions with the first layer, but the performance is bad because then you move to a layer with just 1 neuron. But if you just keep it to decent size, each layer with four neurons at least, what we observe is the more linear regions, the better the performance. And we don't really get to that very large number that we're expecting, but with 32 neurons, we're getting to 10 to the 7th linear regions. And this is where I want to go back to that idea of like silence speaking. Because if we just didn't have a ReLU activation, if we're just passing anything that's calculated forward, this is just a composition of affine functions, which would basically be one affine function at the end. So we go from having a function that would be just one piece to a function that has 10 million pieces. And does a decently good job when we look at MNIST data set, for example. So that concludes prior work. And now we were going to put all of these things together and talk about how you can apply this to network pruning. So for some preliminary experiments, we did notice that the number of linear regions and accuracy go side by side when we start pruning the neural network. So in these experiments, what we did was with reasonably small networks, a little bigger than before, but not much, we just started reducing the density of the network, meaning that the probability of pruning each one of the weights was getting higher and higher. And what you see in green here is the number of linear regions as we make the neural network more sparse. And what we see in blue is the accuracy as we make the neural network sparser and sparser. And we're taking some bold steps here and going all the way to 0.5% of the connections left, just to have a good picture of how these two things would walk side by side. As I mentioned, this is very expensive to calculate. And one of the tricks we use here, which has been used by other people as well, is we just look at the number of linear regions in a subspace, just to get a sense of how big this would be in the entire neural network. For example, in these plots, I'm picking 2, 3, or 4 samples from the training set, and I'm looking at the fine space defined by the samples. In that way, we cut significantly the number of linear regions, and we can just get a sense of how they go up or down as we prune more the neural network. So, and the pruning problem that we're going to consider here is, given a target sparsity, you're set on your mind that you want to remove 50% of the neurons of the neural network. Where should you remove them from? What proportion should you remove from each one of the layers? So basically, we're wondering whether we should remove less from the first layer, perhaps a little bit more from the second layer, or vice versa. So basically, our decision variables here are the proportion that we keep in each one of the layers. And for this experiment, we just use magnitude pruning because it's the gold standard. It's simple, it works, and everybody understands it. So there's nothing sophisticated about how we prune. It's just about how we choose the quantity that we prune from each one of these places. And if we're going to think about how sparsity of the weight, if we're going to think about the effect on the linear regions, we're thinking about the sparsity of the weight matrix. The first thing to notice here is that, I mean, in this case, for example, if we have 5 inputs, and then we have two neurons with 3 layers, 2 layers with 3 neurons each, the first weight matrix is going to be 3 by 5. The second weight matrix is going to be 3 by 3. So the number of parameters is different. And the other and more important aspect is that if we just prune a lot, which is where we like small changes in the algorithm really matter. And then, I mean, just to blow a little bit, if you're just pruning for a little bit, if you're just trying to do the moderate pruning, typically magnitude pruning alone is unbeatable. And we have been trying very hard for a long time. But if you go to very high pruning rates, then you can beat magnitude pruning. So this is where it's competitive to do work, at least right now. So, I mean, if you think about a very extreme example, let's say you have an n by n matrix. If you keep n elements, you can potentially preserve the rank of this weight matrix. Preserving the rank is important because that has to do with the dimension of the output that is coming out. The moment you know that the rank is going down, you know that you're going to reduce the number of linear regions. Now, is it likely if you keep just n weights that you're going to preserve the rank? Not really, right? If you think about it, if you want to keep n elements and have a full row rank matrix, you're going to have to pick these elements from different rows and columns. So there are n factorial ways to do that. But if you think about every way you can pick, you can just preserve n elements in an n by n matrix. That's n squared choose n. And for something as small as n equals 3, this is 6 out of 84. So even for very small weight matrices, very likely we're losing rank if we're so aggressive in how we're pruning. And which means that this pruning mask, we usually talk about pruning mask when we talk about where we're putting the zeros, is definitely going to affect the rank and definitely is going to affect the dimension of the output, which is where things are going to get interesting in terms of the number of linear regions that we can define. And then we came up with this monstrosity, which is an upper bound on the number of linear regions, but on expectation over the distribution of the rank for the weight matrices, for every possible way that you could sparsify the weight matrices. And again, this one I really want you to forget because it's just too much to think about right now. And especially it's a recurrence, there's no closed form here. But just having this bound was enough for us to start thinking about how can we preserve as much of the expressivity as possible. And what we found out is that calculating these upper bounds is a lot cheaper, and it's actually a better proxy for accuracy. So just coming back to that picture that I mentioned before, we were doing counting to understand how the number of linear regions goes down and how that connects to accuracy. That was restricted to subspaces. We had no hope of like calculating for the entire neural network. And then that reflects a specific network. If you're telling me that you counted the number of linear regions in a neural network, you already have the neural network. So you already pruned, you already did your work, right? So it's not really helpful for us. Whereas with bounding, we do need to have this rank distribution. So we have to have a sense of what's going to happen with different configurations. But this is going to reflect architecture. It's going to reflect what's the maximum number that we can get, given different choices of how much we prune from each layer. And at least in the small networks that we worked with, comparing them side by side with the counting, we can see that actually like the upper bound on the number of linear regions on expectation goes down very similar to the accuracy. You can see that they're in the different orders of magnitude, right? I mean, all the plots here in the y-axis, this is the log of the number of linear regions because it's a meaningful number, right? It's never going to exceed the number of neurons. And you can see, for example, for the smallest ones here, we go as far as 4.5 when we're counting, but when talking about upper bound, this goes to 12. So there's a discrepancy here. But the way I like to think about this is when we're calculating this upper bound, we're talking about the potential of the architecture, which can go in many different ways, as opposed to what happens in each one of the neural networks that you can obtain, how many near regions you're going to get in each one of them. And then that takes us to the optimization problem that we try to frame here. And it's yet another objective function for pruning. So what we're thinking is we're going to decide how much density we're going to leave in these two layers, P1 and P2. And we want to look at the upper bound on expectation. So as we vary the density in the first layer, we're going to have a change in the upper bound. And whatever we do with the first layer, there is a reverse effect in the second layer because we have a target sparsity in mind. We're not trying to optimize for that. We don't know what we want. We just are fixing that so that the problem gets a little easier to understand. And what we observed in practice is it's not really about putting all the pruning on one side or the other. What fits very well, it's a quadratic interpolation. You just pick the smallest density you can put in one of the layers, the largest density, that value that would be right in the middle if you just prune equally from both layers, which is also a possibility. You do this quadratic interpolation, you're going to find a fourth point. That point is usually better than the other three. You can do some extra iterations there, remembering again, we don't have a closed form for the upper bound, and you can get some extra improvement. But at that point, this is actually sufficient to improve the potential of these architectures. So here we have some examples of how this works. First, for multi-layer perceptrons. What you're seeing here in the blue curves is the upper bound if you just prune the same amount for all the layers. And what we're seeing in orange is the optimized upper bound when we choose how much we prune from each layer more carefully. And as you can see, it takes a little longer for this upper bound to go down with accuracy. And well, we do see that, for example, these tasks here basically on inputs of 784, for example, MNIST and fashion. And in the first row, we have 2 layers of 100 neurons each. So there's the number of neurons in these layers is much smaller than the size of the input. As the size of the input gets closer to the number of neurons, for example, I have 200 neurons in the next, the difference between pruning uniformly and pruning optimized is not that large anymore, but we still see some difference going forward. And in terms of accuracy, we do see a similar change. So what we're seeing here in blue is how the accuracy goes down as we prune the neural network uniformly in each layer. And what we see in orange here is what happens to the accuracy if we just prune a different proportion. We're not telling what to prune, that's for up to magnitude pruning. We're just saying what proportion should you prune from each one of the layers. And you can see in some cases we get gains of the accuracy of about 14%. And then here we have other examples where we're actually looking at much larger networks, LeNet or AlexNet, and some bigger data sets. And in those cases, we're not looking at the convolutional layers because losing rank in the convolutional layers is very unlikely just by their structure. I have a greater respect for convolutional layers now because they're basically resistant to this phenomenon of losing rank that I mentioned before, just by the way that they replicate the outputs. But if you just look at those fully connected layers at the end of LeNet and AlexNet, and the number of linear regions defined there in terms of the inputs that they observe, we're able to get some improvements as well that also translate in an improvement in the accuracy that we obtain. In some cases, again, for example, we had a 16% for MNIST in LeNet, a 12% for fashion, and like 7% for AlexNet in CFR10. And the bottom line here is, what we propose here, we extend and apply this theory of linear regions to pruning neural networks. This theory of linear regions have been developed for some time. To the best of my understanding, the only application found so far was in neural architecture search, which is basically where they try to figure out which architectures are more suitable for training. And they used counting linear regions as one of the metrics. But that was it in terms of application. So this is a second application to this theoretical concept to understand the potential of neural networks. So what we're doing here is we have a network pruning strategy based on this theory of linear regions. Because this number of linear regions correlates to accuracy, we see over and over that as the number of linear regions go down, the accuracy goes down as well. And we do that by estimating the rank of weight matrices based on their sparsity. And we do that in fully connected layers where the effect is more noticeable. It's possible that we can see some of that effect in convolutional layers. And all that we're talking here is about an upper bound. One possible direction here is we can talk about expected number of linear regions, which does take an entire different type of analysis, but could potentially lead us to a point where with convolutional networks, this would be more easy to get differences. And the bottom line is that sometimes you can really get away with some of this network pruning. And here, there's just a list of papers that I collaborated with some colleagues on some of the topics that mentioned along this presentation, including the last one, which is the talk that you just gave. And, well, thank you for your time. Mateo?
I can imagine piecewise linear function that have a lot of pieces, but all the pieces are almost parallel to one another. Like the overall function is almost linear. And so same with the slope would be 1 plus epsilon, 1 minus epsilon, 1 plus epsilon, 1 minus epsilon. In that case, if I look at just the number of linear regions, then I have the strongest number of linear regions that is probably very, very good. But compared to an identity curve, it's very much the same function. Do you have a way of capturing sort of that effect that you might have a lot of linear regions, but they're pretty much all doing the same thing in a sense?
Oh, that's a good one. I think I have two different answers here. One is sometimes people do want to ensure, for example, monotonicity of the function, because maybe you know that a certain variable, if increased, should make the prediction go up or down. We just don't know by how much. You can use MIP, for example, to certify that. And like there is a whole body of work on, okay, now that we know that it's not monotone, how can we make this a little bit more? So we do see some ups and downs. What we're also observing, and we reset here. And one thing we observe, when we see the examples of how we can actually get so many linear regions, I mean, there's some specific constructions that are going to give an explosive number of linear regions. And there are going to be these ups and downs. The moment you do like one pass of training, that thing collapses. So you do see behavior that changes slightly, and that's going to change from one linear region to the other. And in practice, we're not going to have that many, right? I mean, the upper bounds and the number of linear regions are going to be in a very different range. But it's a good question whether across different linear regions, the change is going to be insignificant.
This came to my mind. all the regions were parallel to one another.
Mm-hmm.
And so I was thinking was, in the end, your function is still continuous, right? So if you have a bunch of pieces that are all parallel to one another, they have to sort of get some kind of regularity in there.
Oh, so what we're seeing there, so it's a great question. But what we're seeing there is just like how that breaks the input space, right? And then the behavior, the output that would come out of that would be like a different visualization, right? And what I understand from the gray area is there is one direction that if you move in that direction, things, I mean, the function is going to grow steadily or decrease steadily. But there's one direction where this happens, and orthogonal to that, the values are all the same. Does that make sense?
Yeah.
So because, I mean, you have that triangle, and that triangle is suddenly split into 3 pieces, right? So you would have something coming like this, changes like this, and then goes like that. But it's just like, it's just not more nuanced, right?
Do you think we could get arbitrary behavior in one of the regions?
What should that figure? Absolutely. Thing with transitions is that then going back takes some time, but we're getting there.
Yes, this one.
Okay.
So on the right? So if we look at the triangle on the right, we end up in a one-dimensional region. So anything that we move along the line where A that is parallel to A, we don't change anything. And then if we take a ray orthogonal to the or parallel to the hyperplane of B, then we get a unidimensional piecewise linear function.
Yeah.
So moving in this orthogonal direction where you actually do something. Now, what I do in this direction has to be somewhat related to what I do on the left triangle.
Yes.
They're basically the same units in the higher layers, but just
yes. Yes. Yeah. There is this idea. I mean, neural networks tend to have this self-replicating behavior. You can think about them as basically fractals, right? I mean, you just have a function that is very repetitive. The way I like to think about this is that basically it's a factored function. It can be very, I mean, it can have lots of pieces, but here and there, you're going to see the same pattern slightly altered, right? Because of something, I mean, whatever happens on the left, on this left triangle and the right triangle might be slightly different, but not by much, right? Because maybe, for example, like this, for example, the output coming from A or the output coming from B could have a different intensity, right? Yeah, but I mean, they could be, I mean, like, let's say the output of B could be multiplied by 2. The linear region would be the same. And you could see, well, the behavior is not that different. That's why I like the idea of thinking about this as a factored representation. It's a small representation, but a representation that fits a lot of stuff. And I do get curious about like whether we can, for example, connect how different linear regions tell the same story. I mean, how they might be talking about the same learned concept. Because when we look at where the training data falls or the test data falls, every input is in a different linear region. So you can't really use the signature to say what you learned. There should be something a little more general than that. I think I took off from where we were talking, but it all comes down to, I mean, it's a sophisticated representation, right? I mean, it's not everything that's represented, but you can represent some very complicated ideas, right? As long as they are repetitive in a certain way. Yes.
With work like this in the future, do you see it as there may be like rules of thumb that people use to essentially pick the architecture, or do you think there's always going to be a place for just trying a bunch of different ones and seeing how they work?
So great question. I mean, I would dream of that. I mean, there is one other paper that has nothing to do with me where they do neural architecture search based on linear regions. But this is one among many theories that has been used to try to explain what makes a neural network more expressive. And there are other concepts and other ways to talk about why this architecture is better than another. I mean, I would be very happy to see this flourishing a little bit more. what I like about this is this aligns very well with my training as a deterministic, discrete, and linear person, especially from integer programming. So I do see how things work here, and I think it's interesting. But there might be other plausible explanations for why things work when they work. But that would be great if we get there.
Anybody else?
Yes.
Oh, thanks. So I wonder if the pruning can be dependent on your data, right? Say you see the data. So I'm thinking, if that's possible, then you can start with the following layer that data at the side. And maybe
Yes. So if I mentioned that there are some techniques. For example, the unreasonably effective one is just pick the smallest weights in absolute value and get rid of them. It bothers me that thing works. But when you start talking about gradient pruning, or for example, optimal brain surgeon, where we're talking about gradients, or like even like about the Hessian of the loss function, then you definitely need the data, and the data makes a big difference. And which also creates a problem. Like, are you going to use all the data? Are you going to use a batch of the data? And yeah, I have a collaborator that she keeps thinking about this. Like, can we just pick? Well, can we in some way pick the data that's most sensitive and just work with that data? It looks like this helps, but we just don't have enough of that to get to a point where we can say, oh, this is a new contribution. But there's something about the data that you choose if you use something like gradient pruning. Were you here when I got to the gradient pruning? Yeah, well, it was a few slides before. It was just like, because where you train the neural network with the loss function, you take the gradient. The impact on the gradient is one way by which you could try to compare things. Oh, we're almost there. Yay, almost there. I don't know if they're that beautiful. So the thing I mentioned was magnitude pruning is just like smallest weights. It works so well. But gradient pruning, now you're looking at the loss function. You take that and you're just thinking, okay, what is the effect of each weight when you take it from the loss function, right? On the loss function when you look at the gradient, right? If I set the weight to 0, what happens? Now that's just basically the weight times the gradient, and you take the absolute value of that, because like you know that the training data is not a fully represented. It's not like everything that you need, right? So only looking at ways. Only looking at the cases where this reduces the loss function might be misleading. And something else you can do is you can look at the second order approximation, which I think is very funny. I mean, we coined this the combinatorial brain surgeon. It was a catchy name, and working on this, we basically had to do heuristics because the problem just gets too large. But in all of these cases, if you're not doing magnitude pruning, you need the data. Yes.
Building on this, if I give you a train model, I give you an input space. Let's say your input lies in the certain architecture, and then I ask you to count the number of linear regions. You can return me a number. Can we start to like branch on the input space? Like if I say I'm only interested in the region of the input space where the first input is in the lower half of this range. Is that an information that you can use to evaluate the number of linear regions for that particular region of the input space?
We can, because I mean, if you can linearly define distribute linear constraints, then we can use MIP for that. Right? Because you can model a neural network as a MIP formulation, and there are some papers doing that. And all you have to do is have to put some constraints on what inputs are allowed. So in this MIP formulation, the trained network is a given. So the weights are given, the bias is given, and what you can your decision variables are the inputs and the outputs that come from it, and whether the neurons are active or not. Then we can count the patterns through these binary variables about the neurons being active or not. So any rule that's linear, you would be able to embed that there, and you should be able to count it.
Some of the upper bounds that you have, can I contribute efficiently?
So the upper bounds, so the upper bounds, you don't need MIP. You just need the MIP if you want to count the actual number. There are other approaches, but I mean, I don't think they scale well for large dimensions just because they start like explicitly manipulating geometrical objects that you're constructing. Does that make sense? So I mean, the upper bounds, they're completely free from the MIP.
So that I can do fairly efficient.
Yeah.
And by fairly efficiently, we can seconds, hours.
Seconds. I mean, if we're talking about like that first theorem, well, if you do memoization, because there is some recurrence going on across the layers, you can get that computed in seconds from pretty much any size. If we get to the second one, then there is the issue that you have to have a probability distribution for the ranks. There is an expensive way that is more efficient, more precise, where we basically sampled lots of matrices to calculate their ranks. There's a cheaper way that's not so precise, where we just use binomial distribution to have a sense of what is the maximum rank of these matrices. That would be a little cheaper. Then for the sizes that we have here, I think we were okay with like doing this in minutes. Yep.
The counting part, examples feel like relatively easy. When we're counting the interval, saying how many different labeling you can have. I'm just wondering if that could be related to, say, studying the generalization.
It is possible. I don't know how precisely. I mean, I think NVC dimension would be like a whole different way to think about the potential of neural networks, right? I don't know how to make the connection between the two. But I imagine this is possible, and maybe it's even desirable to understand if these two metrics are connected in some way.
There's no further questions. Let's thank the speaker one more time.
Okay.